In this video, we solve a question from the topic of the Fourier transform. In this question, the time domain signal is given and we are asked to answer the required information about its Fourier transform without directly calculating the Fourier transform. The question gives the shape of the time domain signal xt, and the first part asks us to find the phase of xj omega. To find the phase of xj omega, we first define a signal yt in this form, from -2 to +2. Now, if we want to express the signal xt in terms of the signal yt, if you pay attention, shifting yt 1 unit to the right results in the signal xt. Therefore, xt equal to yt minus 1. Now we take these signals into the Fourier transform domain. In the Fourier transform domain, xt becomes xj omega, but to find the Fourier transform of yt minus 1, we need to use the time shifting property. According to this property, if a signal zt has the Fourier transform zj omega, then zt minus t0 will have the Fourier transform e to the power of minus j omega t0 multiplied by zj omega. Here, t0 is 1. Therefore, the Fourier transform of yt minus 1 becomes e to the power of minus j omega multiplied by yj omega. Now, according to the second point, any Fourier transform can be written as the magnitude of that transform multiplied by e to the power of j times the phase. So here we can write xj omega as the magnitude of x multiplied by e to the power of j times the phase of x. Similarly, we can write yj omega as the magnitude of y multiplied by e to the power of j times the phase of y. So the right hand side becomes e to the power of minus j omega multiplied by the magnitude of y multiplied by e to the power of j times the phase of y. Now, the phase on the left hand side must be equal to the phase on the right hand side. Therefore, the phase of x becomes equal to minus omega plus the phase of y. Now we need to find the phase of y. According to the third point, if a signal is real and even, its Fourier transform is also real and even. If you look at yt, it's a real and even signal. So yj omega is also real and even. Now, any Fourier transform that's real has a phase equal to 0 because it has no imaginary part. Therefore, the phase of y is 0, and as a result, the phase of xj omega is obtained as minus j omega. The next part of the question asks us to find the value of the Fourier transform at 0 frequency. To do this, we use the definition of the Fourier transform xj omega, which is the integral from minus infinity to plus infinity of xt multiplied by e to the power of minus j omega t. If we set omega equal to 0, then the value of the Fourier transform at 0 frequency becomes the integral from minus infinity to plus infinity of xt, because e to the power of minus j 0t is equal to 1. If you pay attention, this integral is actually the area under the curve of the signal xt. To calculate the area under the curve of xt, we first consider the whole shape as a rectangle which has a length of 4 and a height of 2. Then we subtract one triangle which has a height of 1 and a base of 2. So its area is equal to 1. Finally, 8 minus 1 is equal to 7. And this value is the value of the Fourier transform at 0 frequency. The next part of the question asks for the integral from minus infinity to plus infinity of xj omega. To solve this part, we first write the inverse Fourier transform relationship, which says that x at t is equal to 1 divided by 2p multiplied by the integral from minus infinity to plus infinity of xj omega multiplied by e to the power of j omega t. Now, if we set t equal to 0, x at 0 becomes equal to 1 divided by 2p multiplied by the integral from minus infinity to plus infinity of xj omega. Therefore, the integral from minus infinity to plus infinity of xj omega is equal to 2p multiplied by x at time t equal to 0. Now, the value of x at t equal to 0 is equal to 2. And finally, the result becomes equal to 4p. The next part of the question asks us to compute this integral. To compute the integral, we first consider 2 sine of omega divided by omega multiplied by e to the power of j2 omega as fj omega. Then we consider the product of xj omega and fj omega as nj omega. First, based on the inverse Fourier transform relationship, we write nt as 1 divided by 2p multiplied by the integral of nj omega multiplied by e to the power of j omega t. Then at t to 0 multiplied by 2p becomes equal to the integral of nj omega. So n at t equal to 0 multiplied by 2p is equal to the integral of nj omega, which is exactly the integral that the question asks us to find. Therefore, we need to calculate n at t equal to 0 and then multiply it by 2p. Now we add a fourth point. If two signals are convolved with each other in the time domain, they will be multiplied with each other in the frequency domain. Therefore, if we take nt as the convolution of xt and ft, then nj omega will be equal to the product of xj omega and fj omega. Now we already have fj omega, so we need to find its inverse Fourier transform, which gives us ft. To compute the inverse Fourier transform of fj omega, we first remind that, according to the fifth point, if we have a rectangular pulse in the time domain from minus t1 to plus t1 with an amplitude of 1, its Fourier transform will be equal to sine of omega t1 divided by omega. Then, according to the first point, if we have a time shift in the time domain, it will be appear in the frequency domain as e to the power of minus j omega t0. Finally, based on the first and fifth point, if we choose t1 equal to 1 and t0 equal to minus 2, the inverse Fourier transform of fj omega, or equivalently ft, will be rectangular pulse from minus 1 to minus 3 with an amplitude of 1 as shown in the figure. Now n at time t equal to 0 will be equal to the convolution of xt and ft evaluated at time 0. According to the sixth point, the convolution of two signals z and m is equal to the integral from minus infinity to plus infinity of z tau multiplied by m of t minus tau. Since t is equal to 0, here this becomes f of minus tau. Now, to compute this integral, we need to multiply x of tau by f of minus tau and then calculate the area under the curve of x of tau multiplied by f of minus tau. X tau is the same as xt except that t is replaced by tau, and f of minus tau is actually f of t flipped in time, meaning that the interval from minus 3 to minus 1 is mapped to the interval from 1 to 3, which is shown here in yellow. Now, if we multiply these two together, the region that is obtained is actually the interval from 1 to 3, and we need to calculate the area over this interval. To calculate the area of this shape, we first consider it as a rectangle with length 2 and height 1 plus another rectangle with length 1 and height 2, from which a triangle with height 1 and base 1 is subtracted. Finally, this results in 4 minus 1/2, which is equal to 7 divided by 2. If we then multiply this by 2p, the final result becomes equal to 7p. The next part of the question asks us to calculate the integral of the magnitude of the Fourier transform squared. To compute this integral, we first remind that the integral of the magnitude of the Fourier transform squared is equal to 2p times the integral of the magnitude of xt squared. Therefore, instead of calculating the integral of the Fourier transform magnitude squared, we calculate the integral of the magnitude of xt squared, and then by multiplying the result by 2p, we can answer the question. Another important point is that the product of a signal and its complex conjugate is equal to the magnitude of that signal squared. Now, if the signal is real, the signal itself is equal to its complex conjugate. Therefore, the product is simply the square of the signal itself. As a result, instead of calculating the integral of the magnitude of xt squared, we only need to calculate the integral of xt squared. Now, xt squared will have the following shape, where the maximum amplitude becomes 4. The integral of xt squared is equal to the area under the curve of xt squared. We have the shape of this curve shown here. The shape is exactly the same interval as before, except that the amplitude changed from 2 to 4. We can calculate the area under this curve as a rectangle minus a triangle. The area of the rectangle is 4 multiplied by 4, and the area of the triangle is 3 multiplied by 2 divided by 2. Therefore, the final result becomes 13. Now, if we multiply this value by 2p, the final answer becomes equal to 26p. The last part of the question asks us to draw the inverse Fourier transform of the real part of xj omega. Here we need to remind this point. The Fourier transform of the even part of the signal xt is equal to the real part of xj omega. Also, the even part of a signal can be written as 1/2 of xt plus x minus t. Therefore, if we want to draw the inverse Fourier transform of the real part of xj omega, in fact, we need to draw the even part of xt, which is 1/2 of xt plus x minus t. To do this, we already have xt. 1/2 of xt will have the same shape as xt in the interval from -1 to 3, but its amplitude changed to 1 and 1/2. 1/2 of x minus t is exactly the same as 1/2 of xt, but its interval will be from -1 to -3, as shown in the figure. Now we need to add these two together. If we look at the interval from -3 to -2, the result is equal to 1. In the interval from -2 to -1, we go from 1 to 1/2. In the interval from -1 to 0, with a slope of 1/2, we go from 3/2 to 2. The positive side will be exactly the same as the negative side because this function is even, so we can easily draw it symmetrically. This question included many important points, and in fact, it was a review of the Fourier transform. If this video was useful for you, you can follow our other videos on channel.